All right, we're go for live.
Hello. Welcome everybody. The Mars exploration continues with its newest rover, Perseverance. In July 2020, it was launched using NASA's Atlas V vehicle, and it has traveled more than 7 months and traveled a distance of 407 million kilometers at a speed of 75,000 kilometers an hour. And it is scheduled to land there today. I welcome everyone. First of all, please tell us where you're joining us using the YouTube chat to the NASA's Perseverance landing party. This is NASA's first astrobiologically focused mission. It is also going to try and pave the way for human exploration. I hope you're as excited as we are as we get onto this exciting journey. For this particular event, we have the NASA Livestream, which is going to be playing in this video, and we have 4 amazing panelists who are scientists, engineers, and physicists who will guide us through this landing process and also talk about sort of the building off and landing Perseverance and what it's going to do once it's on Mars. But first, let me introduce myself. I am Nicole Aurora. I go by the name Nick. I'm a PhD candidate in astrophysics here at Queen's University in Kingston, Canada. And I study structures of galaxies by comparing observations from telescopes with theoretical models. Apart from that, I'm also one of the Queen's Observatory coordinator. So we do public outreach. So if you've been here in Kingston, you might have been to our open houses. We have a virtual planetarium. If you've ever heard of Astronomy on Tap in Kingston and you've been to one of the bars, you've seen me frantically running around the bar trying to get things ready. I also participate in that. And we also have a podcast called the Queen's Observatory Fast Radio Burst, which we use to communicate some hot, amazing science to the public. Now, before we get started, I would like to acknowledge that both Queen's University, which I'm not right now on, but my own house, are situated on traditional Anishinaabe and Haudenosaunee territories. I'd like to say that in times like these, I'm honored to be able to use these lands to play, to learn, gather together, even though virtually right now, and share our passion for the cosmos. But also, most importantly, I'm really honored that I can remain safe and healthy in these times. I also acknowledge and greatly respect this territory's significance for the people who lived here and who continue to live upon it, and whose practice and spiritualities are tied to the land and continue to develop relationship to the territory and other inhabitants today. Personally, for me, I'm an international student. I was born in India, which was also a part of the colonized world. And it is really encouraging for me to see the efforts of reconciliations that go on here in Canada. And I hope to learn some of the techniques and things going on here with the reconciliation and take them back home. This event that we are putting forward today to you is about exploring foreign land. We have a rover landing in Mars. And while we discuss this exciting topic of Mars exploration, I hope that we do this in the light of everything we've learned here on Earth today. Okay, so as I said, we have 4 great speakers. And the next part of this panel discussion is just to have our speakers introduce themselves. You get to know our speakers, and then we'll start the main show of actually talking to our speakers. So first on the list, we have Sarah. Sarah Mazrui is a planetary scientist and educational developer, science communicator who has a passion for sharing the wonders of the universe with the public. Sarah, tell us a little bit about yourself.
Hi, everyone. Thanks for having me today, Nick. So as Nick mentioned, I'm a planetary scientist by training. My journey started at an observatory as well, at York University's observatory as an undergraduate student, working there, working with the public, getting excited about looking through the telescope, but also sharing things with others. It's actually funny. My journey into planetary science, I guess, or York in general, started over Mars. It was when Mars was supposed to be at its closest to the Earth. I won't age myself by saying when it was. But, I stood in this really, really long lineup for over an hour to get to a telescope to look through it to see Mars. It was my first time. And they said it will be just as big as the moon. So I was excited. I looked through the eyepiece of the telescope, and there it was, this tiny red dot that looked like a red star. Then I looked a little closer. I think I saw some of the ice cap, maybe, or I imagined I did. I don't know, but I'll be honest, it was not that exciting. But I continued, and then I continued to see stuff that were a lot more exciting. And my journey ended up in space science and planetary science. I studied the formations of different asteroids, formation of the moon, looking at rocks basically and craters on the surface of asteroids and the moon to try and figure out how they had evolved over time. My PhD work focused on the bombardment rate on the moon, the recent bombardment rate on the moon, again, by looking at a lot of craters for a long time. And I continued through science communication, just wanting to share my love and excitement for space with everybody else, trying to make it more accessible for more people to engage with. And today I work as an educational developer at Ryerson University. I work with our STEM faculties in trying to make teaching more inclusive and accessible. And today I'm excited and have my fingers crossed. I've got my Mars donut ready to go. I'm really excited, terrified, but more excited, and really glad to be in great company.
Wow, a Mars donut. I did not know that was a thing. But I look forward to all the science communication that you have here to share with us today about Mars and Perseverance. Moving forward, we have Max King, who's an engineer working on the next generation of space exploration here in Toronto with the MDA. How are you doing, Max? Tell us a little bit about your work.
Hi, Nick. Thanks, everyone, for joining on the live stream. Thanks for being a part of this exciting Mars landing. Like Nick mentioned, I work at MDA, which is the premier space company in Canada. It's the designer and creator of the Canadarm system, Canadarm2, and as well contributor to the ExoMars rover mission, which will be one of the next Mars missions, and talk a bit about that later on. Like Nick mentioned, I'm a spacecraft engineer. I work on sort of assembly and integration of spacecraft. So I was running a little late. We had some issues actually with one of our projects out on the floor. So even through COVID, we're masked up and working together to put nuts and bolts together to get things into space. So I started my journey out in Edmonton, Alberta, out west. And I think like most of us, I started with going to the planetarium a lot. I was thrilled to go to the observatory that was in our town through the TELUS World of Science. And from there, I was hooked on space. And I've been pushing for that throughout my whole engineering or through my education. And I've had the privilege to work here for about 2 years now. We've got a lot of challenges with this mission. It's fun working in an engineering environment like this. A bunch of my colleagues today were talking about 40% success rate is the success rate.
Yikesy daisy.
Mars landers. So we're all looking forward to this today. So thank you very much for having us all here.
Yeah, thank you for being here, Max, and for your time. Okay, next up, we have James, who works as an operation consultant with Stroud International and stays active in the space industry as a project manager with SEDS Canada and is also a member of Space Generation Advisory Council. Tell us a little bit about your expertise, James.
Hi, yeah, thank you again to everyone who's come to the stream, and thanks, Nick, for organizing all of this. So I actually got into space quite late. I had never really considered an interest in space until I entered university at Queen's, and that's when I joined a design team called the Queen's Space Engineering Team, and that got me immediately hooked. We were working on designing rovers, unfortunately not going to Mars, but being tested in a very similar situation in Utah, at the Mars Desert Research Station. So we were designing rovers to compete on a competition there and experience very similar challenges to what you would encounter on the Mars surface. From there, I worked on CubeSat projects with the Canadian Satellite Design Challenge, and have since been involved in the space industry through SEDS Canada, where we are helping students for the next generation get more engaged into the space industry. So trying to connect students to industry leaders and organizing projects to pass on the knowledge from all of our space experts today to the next generation. On the Space Generation Advisory Council, which is an international group, I work on lunar exploration missions. So looking at how could we get people onto the moon. And so I'm really excited about a lot of the payloads on this Mars mission, especially MOXIE, which is paving the way towards getting humans off of this planet onto another.
Great. Thank you so much, James. And we look forward to what you have to offer for this panel. And finally, last but not the least, we have Lauren Edgar, who's a research geologist at the United States Geological Survey Astrogeology Science Center, and has been actively involved in some of NASA's Mars missions. Hi, Lauren. Tell us a little bit about yourself, but specifically, I would like you to tell us how many Martians, the movie questions, do you get about a month or so?
Well, thank you for that introduction, and thanks for having me here today. I'm excited to celebrate the landing with all of you. To answer your question, I certainly get a lot of questions about the book and the movie The Martian, and what we may or may not have seen on Mars and how accurate all of that was. But just to tell you a little bit more about my background first, you can probably tell by the number of times that Nick said geology in my background that I have a background in earth sciences modified with engineering from Dartmouth College. And then after that, I went off to grad school at Caltech and have a master's and PhD in geology. And then I was a postdoc at ASU in the School of Earth and Space Exploration. So given all the geology and exploration in my background, I was able to get involved in the Mars exploration rovers back when I was in grad school. And probably for about the last 13 years, I've been involved in operating rovers on Mars. So got my start with Spirit and Opportunity, and now I am currently on the Curiosity rover team. And I do both research, analyzing the data that we send back, and also actively participating in the operation of these spacecraft. So I'll be able to answer questions you guys might have about the operations that we do, the downlink side of things, analyzing the data that we send back, and also sending the commands to these instruments, and how we kind of carry out both the tactical day-to-day planning and also that strategic long-term planning. So I'm really excited to be here. It's been a good month for Mars, and looking forward to Perseverance and having a new neighbor on the red planet.
Yeah, thank you, Lauren. All right, let's get into the panel discussion. This is a general thing to the audience. If you ever have a question, you can put it in our chat on our YouTube page. Our amazing Queen's Observatory Coordinator, the other Queen's Observatory Coordinator, Connor Stone, and Professor Sarah Satterwhite from Queen's University are monitoring the chat. They will either divert the question to the panel or answer the question for you. So feel free to ask questions as much as you want. Yeah, let's get started. So I have divided the panel discussion into 4 general sections. We're going to try and take about 15-20 minutes for each, keeping an eye on the live stream of NASA, just in case the landing starts. The first sequence is about why is Mars so interesting, and what are some of the current missions that are on Mars. So Sarah, why don't you start us off with that discussion? While you answer that, could you also tell us what's on a Mars donut as well?
Well, the Mars donut, I'm really not sure yet. I've heard there's some chocolate cream inside of it, maybe some glaze on top, but I'll let you know as I eat through it. And now for the first question, you cut off for a second for me. Can you repeat that again?
Oh, sorry. Yeah. So the question really is, why is Mars such an interesting planet to us? And what are some of the current missions that are active on Mars right now? Now that I have a chance to speak, maybe I should say, these are general questions. They're not meant for one panelist. So if anybody else has anything to contribute, feel free to just jump in and lead the discussion. Go for it, Sarah.
Well, why Mars is so exciting, I think there's so many different answers for it, but it is one of the closest planets to us. And I think it's human nature to want to be able to travel to outside of the Earth, even beyond Moon. So a lot of exploration comes with that, but our obsession with it started the first time that astronomers looked through telescopes at Mars and saw these things that looked like lines and canals, and they thought maybe there is water flowing on Mars. So our obsession was to try and see if there is water on Mars, because as we know on Earth, if there is water, there's probably also life. So we've been sending all these missions, and we've been putting pieces of the puzzle together that no, there is no water, liquid water in the form that we know it today, but that Mars did have water, liquid water flowing at some point or another. There are a bunch of missions that are still active. With a lot of the missions, their nominal life is around a year or two, but these rovers really, really last a long time. Well, most of them do. So right now we still have the Curiosity rover, we have InSight lander, and we've got multiple orbiters that are going around. The Hope mission just got there last month. The Tingyang mission just got there last month. So we've got 2 new orbiters at the moment. But we've also got some old timers. We've got ExoMars, which is from the European Space Agency. And I believe we still have Mars Express as well. So there's still a good fleet of Mars rovers and orbiters trying to find signs of ancient life, trying to find signs of more water, subsurface water, anything that could mean there was life, there is potential for us to live on Mars.
Right. Yeah. Lauren, you pointed out you've been a part of these rovers, at least from the NASA side. Could you tell us a little bit about what Curiosity and Spirit and Opportunity have actually established while being on Mars?
Yeah, certainly. So to follow up on the previous question, we really are trying to figure out when and where did life arise in the solar system. And Mars is our nearest neighbor, and having this past record that might have held water is a great place to go and look for that. So when we first sent the Mars exploration rovers, Spirit and Opportunity, that was part of the follow the water theme. And what we found is evidence of, past water on Mars. We found, mostly with Opportunity, we were looking at dry dune fields that intermittently were wet, but that was a great sign. And we found this mineral, gray hematite, that's often formed in the presence of water, which is what drove us to landing in that location. We've then built on that record of not just was water present, but do you have all of the conditions necessary to support life? And that was something that we've been trying to track down with the Curiosity rover. So the Curiosity rover landed in Gale Crater, and we've been investigating this thick package of sedimentary rocks and looking at changing environments over time. And what we found is that parts of Mars have been very Earth-like. We found evidence for ancient lakes and deltas and rivers, and we have dune fields. And what we've been able to find with the Curiosity rover is evidence of past habitable environments. Not just was water present, but all of the building blocks that you would need for life, and an energy source, and minerals that tell us that when water was present on the surface, it had a neutral pH. So if you were there on the surface when this water was there, you would have been able to drink it. So those were all really good signs of past habitable environments. Now Perseverance is going to build on that even more with even more advanced capabilities of detecting organic materials, and then hopefully bringing some of those back to Earth.
Right. Great. Maybe Lauren and Sarah, both to you still, I'm really curious about this water on Mars, and why is water on Mars not there today? Do we have an idea about what happened?
Sarah, do you want to jump in first, or do you want me to?
Go for it.
It's a great question, which is why we both paused as to how do we answer where did the water go. We do know that Mars has experienced a lot of atmospheric escape. We've measured the ratio of deuterium to hydrogen with the SAM instrument on the Curiosity rover to be able to, and of course the geology on the surface tells us that we used to have an environment that could support water on the surface. And these days we have a very thin atmosphere. We can't support those conditions anymore. how did all of that water escape is a great question. These days, there's some water tied up in the North Polar Cap. There's some subsurface ice, but the total water quantity of the content is obviously much less than it used to be. And so this is an area of active investigation. Sarah, do you want to build on that anymore?
No, I will just say this is one of those questions that I love saying, this is what I love about science and about space. There's so much that we still don't know, even about things that we've sent many missions to. It still shows you that some of those big questions are still unanswered, and all the more reasons to send more stuff to Mars and Moon. But we'll leave it for Mars today.
Yeah, this is definitely one of the more exciting things happening when it comes to Mars exploration. James, I want to bring you in over here, especially because of sort of the virtual background that you both, Lauren and you, have. And I'm sure both of them are Perseverance because of the celebration of the successful landing. They look like cars. And I want to ask you, how different is it designing a rover compared to designing a car?
Yeah, I think that's a really good question. Overall, there's, I think, two main differences. One being that on Mars, you don't have all the luxuries that you have on Earth. So there's no paved roads. You don't have the ability to refuel when you want to. And if something breaks, there's no auto mechanic nearby. So everything that you design on these rovers is more rugged than you would ever need to on Earth. If you can see on my background photo, one of the big pieces there are the wheels. So the Perseverance rover here has had a redesign above the Curiosity wheels, which are more rugged. So the rocks on Mars are incredibly jagged, and they're very hard to roll over. And so the wheels themselves aren't like a car where it's rubber and it's soft, because if you pop a wheel, then there's nothing that you can do about that. So these wheels have to be very hard themselves. And so the way we design them now has a thicker rim and better treading to better grip onto the rock on Mars. If you also think about a car on Earth and versus on Mars, we can't operate this rover live. It's all programmed remotely and almost done autonomously. So the speeds that we're driving at are incredibly slow. On Earth, we can move a mining vehicle on the order of kilometers per hour. Here, it's more along the lines of kilometers per year, and it's much, much slower.
Yeah, so let's actually bring in Perseverance now, and I want to bring in Lauren and Max. Max, you're one of the last panelists to speak, but you're definitely the exciting one as well. I want to ask, it's a two-part question. The first question is, what are some of the challenges that previous missions, so Curiosity, Spirit, Opportunity, have had? And then how is Perseverance going to be different? What have we learned from those missions that we're now putting into Perseverance?
Sure, I'll tackle the first part of past obstacles, and then I'll turn it over to Max. So as James just said, there's been a redesign of the wheels. And so with the Curiosity rover, one of the things that we noticed is that we were experiencing a lot more wheel wear earlier in the mission than we anticipated. So we're actually poking holes through these aluminum wheels at much faster rates than what we had tested out on Earth previously. What that told us is that the rocks on Mars were really well cemented. There's actually in Max's background, you can see an example of some of these sharp, pointy rocks that have been shaped into points by the wind. So we're puncturing the wheels. So we had to change our drive strategy to kind of drive through these sandier areas to protect the wheels a bit more. On a similar wheel story with the Spirit and Opportunity rovers, the Spirit rover actually had an issue with its front right wheel and stopped being able to rotate. So we were kind of dragging that through the soil and dirt as we were driving. We're kind of driving backwards and dragging it. And by trenching like that, we actually uncovered some really interesting bright soil that had the highest sulfate concentration of anything that we had seen. So there's always these obstacles to overcome, but they sometimes lead to important new discoveries. And of course, as James said, we've built on those past lessons, and Perseverance has some nice thicker wheels and more of what we call grousers, those treads that you see across the wheels. So hopefully we won't have any wheel issues on this rover.
Yeah, thank you, Lauren. Before I get to you, Max, we have the lead on entry, descent, and landing on the live stream on NASA. So let's just listen in and see what's going on with the NASA feed. Zach?
That supersonic parachute. based just on navigated velocity. But now Perseverance has the smarts to figure out where she is and deploy that parachute at just the right place to make sure that we shrink where we could come down. That actually reduces the area, that error ellipse, where we can come down on the ground, from something that was on the order of 15 miles long by 12 miles wide for Curiosity to about 5 miles long by 4 miles wide for Perseverance. So that's quite a bit of reduction. Second, the next piece of technology that's helped us land there is terrain relative
navigation. It says
navigation.
that we're listening on, it's being streamed on YouTube, not for us.
We've taken pictures of the ground as it's been coming up.
So I guess we'll be guessing.
Anything with them. This time, Perseverance is carrying a camera to take pictures, but also a kind of second brain to help it figure out what those pictures are telling it and match it up with an onboard map from a satellite. That allows it to figure out exactly where she is. Suddenly, then, she can then fly to safe spots that are nearby once she really knows where she is. It allows the site to not have to be as flat and boring as a pancake as some of our past sites have been, the entire area we could come down. Now we just need little pieces of that site to be small enough and safe enough for us to land in safely and fly there after we've gotten rid of the parachute.
And we also have a social media question coming in. Sansakari14 on Instagram is asking, how does the sky crane decide where to move itself after the payload lands?
After the payload lands, after the rover touches down, the sky crane, the descent stage, which is that rocket-powered jetpack above it, the first job, of course, is to make sure you don't hurt the rover. So it'll turn forward or backward so that the engine plumes don't pass over the rover. So it'll come up and start to turn. And it'll go in whichever direction is closest to north. So it can either go forward, if that's the way north is, or go toward the rear of the rover, if that's where north is. And it'll fly about 1/3 of a mile or so away.
Thanks for talking to us today, Al.
Thank you, Zach. We'll get back to our panel now. Just waiting for Zach to cut it off. Okay, great. So Max, lead us off. What are some of the new things on Perseverance when it comes to Mars mission? How's it different and why is it important?
So one of the exciting things that we were just hearing from there by the EDL lead, Introduced Landing lead, talking about the sky crane technology. I know James knows more about Mars descent and landing and stuff, so I will let him comment on most of that. But the keyword in space, a lot of us think it's state-of-the-art. Coupled with that, it's also reliability. What do we know works? That usually gets the most credit in any design meeting. Anytime you're proposing something new, it gets some eyebrows raised. Why can't we do what's worked before? So this is kind of a funny thing that's at odds in the space community. We always want to be pushing the boundary, but we do have to rely on things that we know will work. And reliability is key for all of these systems. How do we know that all of the pyrotechnics, all of the explosive bolts that will blow on these systems will go at exactly the right times and provide the right amount of force as it separates from the orbiter and begins descent. So one of the big things, if you've seen different landers, is the landing techniques. If you go back and watch obviously there's no footage of the actual landing, but you can watch CGI demonstrations of the Spirit and Opportunity rovers landing on Mars. And to me, that almost seems more terrifying than the sky crane ones, where you had all these essentially beach balls inflating and this tumble as it bounced down around the Martian terrain. Quite terrifying. I know one interesting comment about the wheels. I think I wonder what the effect of reduced gravity is on the rovers as they sink. They sink not as deep into the Martian soil. That's a question I've always wondered. So I want to ask Lauren or Zara that maybe a little later on. But the reliability is everything for these missions. And I think Zara touched on it as well, the mission lifetime. They planned for a year or so, and then they end up working for, in Spirit and Opportunity's case, over 10 years, or Opportunity's case, over 10 years. And so that comes down to a lot of the care and precaution in the design of a huge amount of conservatism, making sure that you're building something that's going to last as best as, like, you can be fully confident it will work as at its peak for a full year, and usually these things last longer than the engineers estimate, but there is full confidence that they can last for that single year. As James said, there's no repairmen on Mars yet, so we're going to be a while away from sending homemade rovers, I think.
Yeah. Well, thank you, Max, for that. Yeah, that brings us to the close of our first segment of this panel. And I'd like to take a few questions from our audience right now. I've been just informed that NASA's about to transfer to the EDL procedure. And as soon as that happens, I'm sorry, I might have to cut you off. But yeah, let's take some questions for now. The first question comes from Christopher Meyer, who's asking, how far below the surface will Perseverance be able to probe? Will it be making direct tests for life? So yeah, let's have either Sarah or Lauren on this.
Yeah, so I think in terms of the drilling, we'll only be going down, maybe 10 centimeters or so. I'll have to double check on that, but it's actually a very short distance in terms of what we're actually sampling there. And then there's other ways of inferring information about the subsurface through some of the other instruments. But we'll mostly just be looking at what we have on the surface and then some short cores that we'll be able to bring back.
Yeah. Great. I want to get back to sample collection as well. You kind of hinted to it. But before we get back, some questions are coming in for the engineering team on this panel right now. And one of the questions comes from Matthew Stugel, who asks, how big are the teams that design these rovers? And can you give an example of positions of people involved here?
I don't know, Max, if you want to give some information there from the work at MDA.
Yeah. So these are incredibly multinational. They're international teams. There are teams that involve numerous companies. So, for example, I alluded to MDA has worked on the ExoMars rover, which will be launching in 2022. And so there's companies that span, there's obviously huge investment from the United States. NASA will lead this effort of this Mars rover, but all of the instruments are often built by each of the payloads, which we'll talk about some of them, I'm sure, in detail. Those will be built by separate companies. They'll maybe have Airbus, say, will design one specific payload, or a university lab will be working, a principal investigator will work on one payload with another company. And so you'll typically have at least five like large aerospace companies working together to create these enormous projects. And you're employing on the order of 1,000 people directly working, who can directly say they are working on a Mars rover. And the team size varies. I think if you were working on, say, instrument, that might be a team of, say, like 50 people might be working together to build that. And within that group, you'll have engineers, you'll have software developers, you'll have all sorts of additional positions that aren't necessarily technical, but you'll have people who are doing PR management, that kind of thing, or even just something like shop floor coordination, making sure all the pieces are in the right places for engineers, technicians to do their jobs safely and properly. So there's a line I like. It's that Bill Nye says it all the time, like space brings out the best in us. And I think building on that, I like to think that space is for everyone and it takes everyone. So I think if you're interested in getting involved in these types of projects, it is closer than you would think. I think for our Canadian audience that's on here, if you are interested ever in working in the space field, I will just plug this. There's, on the Government of Canada website, there's a database of the Canadian space companies, companies that in Canada that directly do work involved in the space sector. So I do encourage everyone to Google and look for that. But that's my assessment of team size right now. James, do you have anything to add?
Yeah, I think you had a really good comment there that these teams, even though this is a NASA-run mission, the teams do come from all over the world. I think it was Norway developed the RIMFAX instrument, and the French CNES developed the SuperCam. So it really, when you talk about what team is working on this rover, it quickly can expand depending on what exactly you're looking at. The wheels themselves that we talked about will have their own team, the suspension mechanism, etc. So everything's a group effort.
Yeah, thank you, James. I want to continue with you here over with the landing as well. There's a question by Manraj Gaming who says, what damages will be caused to the rover if the landing doesn't go quite right? And I know we don't want to venture too much into that topic. The landing's going to go perfect, but just in case it's a little bit off, what damages are we looking at?
Gonna knock on wood right now. It'll vary. So as the rover's coming in, so when it first hits the atmosphere, the angle that it's entering the atmosphere is going to be very critical. If you're going in too shallow, if you've ever skipped a rock on water, it'll happen the same way, where the rover will actually skip off of the atmosphere. That is, in that case, it won't be going to Mars; it'll be going somewhere else in the solar system. But if you go in too steep, on the other hand, you'll start crashing into the atmosphere incredibly fast. And so if the rover doesn't burn up, like you think of meteors coming onto Earth, then it won't have the capability to slow itself down fast enough before landing. So you kind of have these two extremes early on. And then throughout the whole EDL process, there's always a risk of a system failing. But the engineers on the rover teams have gone through, this is where we talk about the conservatism in the design. You can't just let one system fail, causing the whole mission to fail. Usually these are designed so that needs to be 2, 3, 4, multiple things have to go wrong before the mission success becomes compromised. But EDL is definitely the most high risk portion of this process. We just don't know enough about Mars to design well, so everything just has to be over designed.
Yeah, I see Sarah taking a very deep breath as we talk about EDL. We're going to have time for EDL as well. We're about maybe 20 minutes away, and I want to get into sort of the payload, as Max pointed out, that Perseverance is carrying. What is it going to do? So I want to first talk about, maybe, in my opinion, the most exciting thing, and that is the sample collection. Sarah, why is sample collection so important? Why do we want to do it?
Yeah, so until today, the only rocks or samples from another place outside of the Earth that we've brought back are moon rocks. We do have Martian meteorites that we have found on the surface of the Earth, but that's kind of, I call it working backwards. You find the Martian meteorite, and then you have to try and figure out where on Mars it could have come from. But this time around, we've actually selected a place where we want to go to and pick those samples. Now, what makes Jezero craters really exciting, as we've talked about, is that we think that it's an ancient lake. So it was a lake at some point or another. 3.5 billion years ago, there was a river flowing into it, leaving behind sediments. And like we see here on Earth, those would be the places where microbial life could have existed. So now these samples, we believe, might contain some signs of ancient microbial life. So Perseverance will be going there, collecting these rocks, setting them aside. And I'm really, really hoping that the follow-up missions will happen. We will have other missions that will go and bring back these samples, but we've never done that before. We've never collected samples to bring back. We've always had the set of instruments on a rover where kind of work as our eyes and hands to sort of analyze and collect data, but nothing beats being able to have them here on Earth in our laboratories that are a lot more advanced and detailed than what we can put on a small rover to Mars. So it'll be really exciting to have those back. And I believe Canada is going to get a piece of those samples as well. Professor Hurd is one of the 10 people, I believe, selected to work on selecting these samples. So I think because of him, I would say, we might get a piece of the samples or a little bit of the samples. So I'm really excited. We'll get some here in Canada as well.
As
Yeah.
a
Or-
University of Alberta alum, I do have to say a shout out to Dr. Chris Hurt. That is a fantastic wealth of space knowledge we have in Alberta, thanks to him.
Yeah, and Lauren, I want to bring you in about sort of, because you're directly involved with NASA's Mars missions, about sort of the technicalities of collecting these samples. So first of all, how are these samples collected, and are they just left on the surface for recollection? Is there a special place? Lead us a little bit into that.
Sure. So actually, one of the key differences between the Curiosity drill and the Perseverance drill is that the Curiosity drill kind of uses rotary percussive drilling, and it makes the drilled sample into a powder that we can then analyze with some other instruments. What's different with Perseverance is that it's actually going to be cutting. So you'll be getting a full, complete rock core out of some of these. And then those samples, so we have about 43 sample tubes, and then there's 5 extra tubes that Perseverance has that are called witness tubes that have different chemical compounds to be able to make sure we know the conditions under which these rocks were collected, make sure that if there is any contamination from propellant or anything else, that we can account for that. So these samples will be collected and stored in the belly of the rover, kind of on the front side. And then right now, the understanding is that it's up to the science team, the time and place where this cache will then be left for future Mars sample return. I do know that there's a lot of interest in terms of the traverse. Let's say you land kind of out in the flatter lake bed area, which looks nice and ideal for landing, of at least getting through some of these deltaic deposits, shoreline deposits, anything you might have from the crater rim or some of these more ancient rocks, before leaving that sample cache, because you want to make sure that you have the most representative rocks possible for a future mission to come and return. So there are some hypotheses about where that location might be, but it's still going to be up to exactly what happens, where do we land. The events of today will certainly help to shape that.
Okay. Yeah, I want to get very specific on something that you said, which was the witness tubes. Could you tell us a little bit about those witness tubes? What are these things? I hear there's stuff already in those tubes.
Yes, I have to admit, I don't know the exact chemical compositions that are in those tubes right now. That might be something, I don't know if others on the line have looked into the details of those compounds. But essentially, want to make sure that we understand any contaminants, like I said, from potential propellant. Things will be able to have a different range of pH and react with soil and air samples, just so we know the exact conditions. But I don't know the specific details. Anyone else want to comment on what those compounds are?
Who's an expert in chemistry over here? We need a fifth panelist, I guess.
I can sort of speak to it. Similar to how handling a lot of samples on Earth, we want to know that we're not accidentally contaminating the samples. So when we bring back a sample from Mars and we say, oh, there's a trace of plastic in this, that's strange. Could it have come from the rover? And we want to know that. So every material that gets sent on that Perseverance rover has been cataloged, and these components in there will have chemicals from, say, the propulsion system, any organics from Earth that we might have accidentally brought over, likely any materials on there, just in case, so that when we detect something, we can confirm, yes, this actually came from Mars and not from something on the rover that could have contaminated it.
So I want to continue the sample caching, and yes, Max, I want to bring you into the sample caching as well. We have to bring these back, and you're involved in some of the future missions to Mars, and I want to know how easy. I'm assuming that you would have to launch something from the surface of Mars. How easy is it to launch something from the surface of Mars, given the different environment that Mars hosts?
That's a great question. So Mars sample return is an incredible problem that we're going to solve in the 2020s. I do want to add a comment on planetary protection briefly, which is related to the topic of contamination. That NASA and their contractors will take very seriously all the cleaning of all of the surfaces in these rovers so that there's no contaminations they're bringing. And one consequence of this that I think is really fascinating is that we've found in these clean rooms where we build things that are perfect, like very sterile environments, they've found bacteria that have been able to survive in these incredibly sterile environments in NASA clean rooms and clean rooms around the world. So I think that's a really interesting encouragement for finding life out there in the universe. Life finds a way. So, but the sample, Mars sample return. So this is a phrase sort of for an overarching goal that Mars 2020 here is kicking off, that the Perseverance rover is the start of. And that is this mission to try and, as Lauren mentioned, drive and collect samples and capture them into these ceramic containers that can be left on the ground. And then another mission called Sample Fetch Rover, which will launch hopefully sort of in the mid 2020s, will drive around and essentially pick them up and bring them back to a centralized location. So you have the scooper, and then the driver, the fetch rover. That's the next mission that's in the works. And then you also have to bring them back. So as you mentioned, that involves getting something off of the surface of Mars and back into space and back to Earth. I really encourage everyone to go watch even the rocket launch of this mission. And you can see the incredible amount of infrastructure there is around a spaceport. The incredible amount of infrastructure it takes to launch something into space. And we are going to be trying to build something of that sort. Obviously, it will not be as sophisticated, but the bare bones version of that on Mars over a next series of missions, hopefully by the end of the 2020s, to have those samples recollected and launch them back into space and possibly carry on straight from there back to Earth, or rendezvous with another orbiter that's already there and have that take them back to Earth. So this is an incredibly complicated mission, this sort of overarching goal of Mars sample return. And there's a lot of focus right now on the Lunar Gateway, and I think rightfully so, and getting humans back to the moon and returning a presence to the moon. But for me, one of the more exciting things in the 2030s will be bringing a sample back from Mars, bringing a piece of another planet back home here.
Yeah, that's a great point. And yeah, I want to point out that very recently we brought back some stuff from the moon. The Chinese Chang'e 5 mission brought about 4 kilograms of things from the moon. And the way they did it is having another orbiter that reconvened with the launcher from the lunar surface. Yeah, and so I want to continue on this, even though I really want to talk about the oxygen creation that's going to happen with Percy, and sort of the cameras and selfies that it's going to take. But I think the last question here, and Max, you can lead us off into it, and then maybe Sarah can pitch in as well, is there's a helicopter on Perseverance that I think is going to test this, right? Because the rocket, I presume, is supposed to be much smaller, because we just don't need enough power given the atmosphere, right?
Yeah, so that is a great, so 2 parts there, the helicopter that is a part of this mission, and then, what will that teach us? What will that tell us about Mars? So all the science we do on Earth is relatively very easy to do. You can send a grad student out with a thermometer to measure the temperature 800 times a day if you need to. But you don't have that luxury somewhere on Mars. So with this helicopter, the idea is, how can we figure out how can things fly on another planet? We've mastered building aircraft here on Earth pretty well, but that all depends on things like, what is the atmosphere made of? How dense is that atmosphere? What are the temperatures of that atmosphere? How windy is it? Mars has a much thinner atmosphere, so we won't have quite the same lifting force that you could have using a helicopter. But with flying a rocket through that less dense atmosphere, you're getting far less pressure from the air pushing on your rocket. So Mars, for getting a spacecraft or for getting a craft from Mars surface to the orbit of Mars, is hopefully going to be easier than it is on Earth. We'll have to use less propellant. It won't have to go as fast to break free of Mars' orbit. Mars is, someone else might have the better figure than me, but about almost a third of the gravity that there is on Earth.
Yeah.
So you won't have to.
38% to be precise.
38%. Thank you, Nikhil. We're all scientists and engineers here. We're all about being precise. So you'll need to use less fuel. And so this helicopter is just incredible. This is going to be the first thing we're going to have flying on another world. And I don't know if anyone has additional details on the helicopter. I would love to hear from someone who does. But the great thing about it is we'll learn how can things fly. We'll have better understanding of the atmosphere's effect on how things will fly on Mars, hopefully for future missions. And there's also hopes for having these kinds of probes, these kinds of drone helicopters on future missions to the outer solar system as well. So this is going to be history if the helicopter works. So hopefully we see one on Titan in about a decade.
Yeah. Yeah, Sarah, I want to bring you into the conversation as well over here. One of the things that is being asked on our YouTube chat quite a bit, which has nothing to do once again with Mars landing, is how did the donut taste? People have seen you take bites of it. What's in it?
It's good. It's a little too chocolatey for me, but it's not bad. It's not bad. I'm seeing on Twitter, people in the US have them by the dozens, but I know here there's a limit of 2 per person. It's a good limit. It's too chocolatey for more than that. But I will say that the official Mars rover landing snacks are peanuts, Lucky Peanuts. So if you've got Lucky Peanuts, now's the time to get them out and start eating them. Or even if they're not lucky, I'm sure they will bring some luck for Perseverance. And we'll probably, as we see some footage from the mission control room, we might see some individual packs of peanuts this time instead of the peanut jar going around. But we'll see that. But on the topic of the helicopter as well, I'm really excited. I feel like it's one of those, it's more of a technology demonstrator this time around. I think sort of like the first time we sent stuff to the moon and Mars for the first time, it's just like, how is it going to work? But I think its first flight is scheduled for a month from now, if I'm not mistaken. So it will be really cool to see what it does in a month. I've already assumed that landing's going to go well, and I'm already there a month from now to see the helicopter.
Yeah. Well, we are getting closer and closer to that EDL time, and we have lots to talk about still. Wow, Perseverance is an exciting instrument. I want to get to the oxygen creation now. And maybe, Lauren, you can lead us off into sort of the oxygen creation. Why is it so important and how is it being done? So that's MOXIE, right?
Yeah, so the MOXIE instrument is going to convert, so Mars's atmosphere is mostly carbon dioxide. And so the MOXIE instrument is going to convert carbon dioxide into oxygen. And the reason why this is really important is for future human exploration of Mars. Rather than having to take everything with you, if there are resources that we can find on the surface or generate on the surface, that's going to significantly reduce the mass that would be required to send humans to Mars. So yeah, really excited about that. I don't know if some of the engineers want to talk a little bit more about the details of that process, but looking forward to this other technology demonstration as well.
Yeah, James seems to have something to contribute over here. James, go ahead.
I think this just also goes back to the sample return, trying to launch something off the surface of Mars. Oxygen is often used as a fuel source for rockets. So being able to have your own fuel generation on the surface of Mars saves you from having to cart all that fuel all the way over there. You sort of have a refueling station there already. So incredibly excited to see. I think MOXIE is only supposed to run a couple times for short 1-hour bursts. So this is another one of those technology demonstrations where we're just trying to understand how hard is it to break apart carbon dioxide into oxygen, and what are the power requirements? How hot does it need to get? There's a lot of questions that are on Earth seem very simple, but on Mars just throws extra challenges.
Yeah, absolutely. Yeah, I think it's the same thing with the sample return and Moxie. We want to bring things back over here because we have elaborate laboratories in all parts of the world that we can actually use to do very sophisticated experiments. Getting them onto Mars, much more complicated. And so bringing things back is definitely going to be very exciting. Yeah, so oh, NASA's Lucky Peanut is on the stream right now. There's a jar. It's not a packet right now, and they seem to be. Yeah, just for fun, Zach, can we zoom in and listen into this very quickly?
Well, speaking of the experience, how did the Perseverance team keep the tradition alive this year?
Well, this year we passed out little packets of peanuts to the team, and they can sneak one peanut in their mouth as part of to keep the tradition alive. But you know, this is part of the COVID experience, but we can't leave this one undone. So this is what we're doing, and this is going to help us land safely.
All right, thanks, Rob. I have some questions for you a little later on.
All right, thank you, Zach, for that. Yeah, we are getting close to landing, and let's actually get into the complicated and anxiety-inducing topic of landing on Mars. James, how hard is it to land on Mars?
I think Max brought up a stat earlier of 40% of Mars landings have been successful. So that's kind of where we're sitting at now. Though NASA's had a very good track record, especially now with using the Sky Crane for the second time. We know a lot more from last time with Curiosity, so there's a lot more confidence here. But Mars landing is sort of the worst of both worlds in terms of planetary landing. You think about the two extremes, Earth and the Moon. On Earth, we have a nice thick atmosphere. So when something comes in, we can just use heat shields and parachutes to slow us down enough, and then we can get a soft landing. So you don't need anything fancy. It's all statically driven. On the Moon, where there's no atmosphere, you have to use rockets. So when the Apollo landers were going down, they brought rocket fuel and propellant and had a powered landing on the surface. Mars, on the other hand, requires both. So we have an atmosphere, so that means we need to use a heat shield or else we'll burn up. But it's not thick enough to actually slow us down fast enough for the surface. So we also have to bring in fuel and propellant to get us down. So it ends up being a challenge where we have to convert between two different landing systems there. I'm not sure if Lauren or Max, you have other things to add.
Yeah, so one of the really cool things I'll briefly touch on and then turn it over to Max to talk about terrain relative navigation. One of the other complicated parts and really exciting parts of this landing compared to others is using what we call terrain relative navigation. So the US Geological Survey was involved in creating some really precise maps of the landing area that are actually loaded on board the computer of the rover or of the landing system. And basically it's going to take pictures of what it's actually seeing as it's landing and compare to the onboard very precise version and help to avoid hazards and make some of those adjustments on the way down. Max, do you want to add to that? It's a really cool technique that's being tried for the first time.
I was going to say, I do feel that in these landing conversations, and I am sure both you, Lauren and Sarah, have much more experience with this huge process of picking a landing site. But I feel like from wearing my hat on a design team, I'd be staring at the flattest and most boring part of Mars over and over again and being like, that's where we're gonna go. That's where we're gonna go. And I think they had a similar backs and forths with the Apollo landings, sending humans to the moon. And your first approach, you're probably not going to pick the what I would imagine might be a more geologically interesting and productive area to go, which brings us back to a very important point that does come up in all these conversations. Like, are these missions worthwhile? Is this an important thing to do? So the onus is on the engineers especially to be creative and to find a way to make the scientists happy, to do the best we can to make sure that the science that comes out of these missions is as impactful as it will be. A brief note on other sample return things that have come back to Earth. The Hayabusa 2 mission that returned a sample from an asteroid as well as the OSIRIS-REx mission, which is on Bennu, that MDA has helped be an incredible, make a successful mission. CSA's Tim Haltigan was talking about it at a panel a few years ago and did mention that, this science isn't about now. It's not about, what papers we can publish and what we can learn in 2021 or 2022. It's that students and teachers and everyone will be learning from the discoveries we make using this technology still 30 years from now. That these kinds of things are investments that you have to think about for decades long, not just the mission lifetime of 1 year, 2 years.
Yeah, so Max, you talked about flat landing surfaces, and I want to bring Sarah into this. Sarah, tell us a little bit about where the Perseverance rover is landing, and it's been dubbed as one of the most technical landings ever into the Jezero crater. And so I want to know, why is it that we wanted to land in such a technical spot?
That's a great question. And I'll just sort of build up on what Max has already talked about. When it comes down to landing site selection, it's often a big fight, even amongst scientists, before it even gets to the engineers. You're often in a room with 100 other scientists, and everybody is very, very excited about the place they want to go to. But we always, in planetary science, we have a list of priorities or decadal priorities and questions that we want to answer, both not just within understanding more about Mars, but about the solar system in general. So wherever we send something, we want to be able to maximize the number of questions that we can answer as safely as possible. And it's always a little bit of a push to get to go to maybe a bit more of a risky place, and it's just like, well, come on, engineers, just make it happen, make it land safely and rove around safely. And I think the beauty of it now is that we have so much data from Mars that we can really map the surface, really know where Perseverance or another rover is going to land. And right now, Perseverance is going to land with its eyes open too, due to the automated navigation system that it has. So it's still going to look around and try to find the safest spot within the ellipse that we've selected. The Jezero crater, again, like we said, we think it's an ancient lake. So it's had water at some point or another. And if you were to pick one place, or if you were going to put all your eggs into one basket and select one place that might lead you to signs of ancient microbial life, this would probably be one of the highest ranking places, again, on sort of a surface where we can land safely. And going back on what Max said about the samples that we bring back, it's very true that we're not just doing this for 2021. Even with the Apollo samples that were brought back 50 years ago, it's not like it got back to Earth and it was just handed out to scientists and engineers to go on and do research on. A lot of it has been kept in very pristine conditions, locked away, and every year scientists and engineers have to write a proposal to explain why they should have a tiny piece of the sample so that they can do some new research on. And it's because technology has changed and improved so much over 50 years. So I'm assuming that if we were to get some of these samples from Mars, we might go through the same process. Some of it might be kept safely away for future years, again, to bring in the future generation, but also for technology that's going to be more advanced.
Yeah, thank you, Sarah. Lauren, you want to add in something as well, and I have a question for you coming in from the audience as well, but I'm being told by my producers in the background that we're getting very close to the entry. It's about 14 minutes-ish, and Perseverance will be shutting off its transponders very soon. So I just want to say that we might cut to the NASA stream any moment. But before we do that, we have a question from Nancy Lormer, who asks, is it possible that the surface might be too soft? What if the rover sinks down into the surface? Lauren, go ahead.
Yeah, great question. That was certainly something that we were initially concerned about with the Apollo missions. But with Mars, we actually now have a pretty good idea of what the surface is like. You can use things like thermal inertia to figure out how much bedrock there might be versus sandy cover, kind of getting at grain size and cement of the materials that we'd be landing on. So we're not too worried about the wheels sinking in too far into the sand. And we've also done a really good job of mapping out the surface. And by that, I mean, looking at the different types of geologic units that might be present. You can use, texture and the brightness of the terrain and, some of these other geologic methods to figure out what types of materials you'll be landing on. So the team, the Perseverance team did a mapping exercise. There's also a recently produced USGS map of the landing area. And, hopefully we'll be landing on some interesting bedrock and exploring from there.
Yeah,
and the other thing
thank you. Go for it, Lauren.
The other thing I was just going to add to the previous conversation about scientists and engineers coming to consensus on a daily basis. You guys had kind of touched on, this is a really delicate balancing act, and it's not just for landing, but actually the operation of the rovers too, that the scientists are going to be pushing for complicated but really interesting locations to go to, and the engineers need to say, here's what we can do within our safety constraints, and it's kind of this back and forth, give and take. But pretty impressive that on a daily basis on Mars, and now soon to be on multiple places on Mars, that you have to come to a consensus plan together.
Thank you, Lauren. We're about 90 seconds, a minute to the crew stage separation. So Zach, can we listen in about now?
From entry interface.
It's getting exciting. I have to admit, I am quite anxious, but very hopeful that this machine is going to do what we asked it to do.
We're seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
We're continuing to receive tones from Perseverance, standing by for crew stage separation. We have indication that crew stage separation has been confirmed by the spacecraft.
Great. The crew stage separation has happened.
In about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with its entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Thank you, Zach, for that. So we have about 9 minutes before the excitement begins. And Zach, Lauren, I want to bring you back in here, and maybe James also contribute to the conversation. But let's start with Lauren. What is crew stage separation, and what just happened?
Yeah, the gist of it is that the crew stage that was keeping the spacecraft, basically all the way from Earth to Mars, has now separated. So now we can turn it over to the landing system. James, do you want to talk about any more of the details?
Sure. I think one of the things that they had mentioned that was interesting there was the tones that was being broadcast out. So throughout all this, we're tracking how the rover is doing based on a set of just beeps. If you think of like an old telephone, the dial tones, because there's so little capability for communication. So we're learning all this information just from a beep that the rover can give us. When the cruise stage separates, this is the critical point where we're trying to get into the atmosphere at the correct angle. And so if you'll notice on the simulation, the rover is actually rotating. And so that we purposely keep it rotating during flight to make sure that its direction is pointed where we want to, it's aligned well. But as soon as this cruise stage separates, we'll soon actually stop the rotation and try to unbalance this, the rover, so that it actually enters at the correct angle onto the atmosphere. And we use the unbalanced shell to actually steer the rover while it's in this heat shell. So where it's weighted a little bit more, it'll push against the atmosphere, and it'll actually be able to turn and use that to the terrain map that Lauren was talking about to actually figure out where it's going and steer itself as it's going in.
Yeah, I'm looking at the NASA Livestream right now, and it looks like it has reached, it has turned itself to the desired altitude. So everything seems to be going good. We're about 7 minutes and 30 seconds from entry. And let's talk about the dreaded topic of EDL. Max, I want to bring you into it. Curiosity did similar things. So how confident are we based off of Curiosity? And why is this thing so nerve-wracking every time?
I won't speak much on this because I do think James has much more to add on this. But the sky crane tech, which the lander will be using, this sort of jetpack coupled with a crane to lower the rover down to the surface, was used before on Curiosity. So if you're looking at that success rate, that's 100% success rate right there. That's not good science using a sample size of one, but we'll be really hoping that this will work again. If it does not, there'll be sort of, we'll be investigating, or the engineers and teams will be investigating this for months to come. And it will be incredible to know if, was it just an incredibly lucky fluke before? I don't think it was. These systems are tested incredibly rigorously for decades. The Curiosity Sky Crane proposal was first put forward over a decade before that ever arrived at the surface of Mars. So these ideas are not pulled out of a hat. They are tested very rigorously for many years so that there is very little margin of error when you arrive at the planet, as much as possible. Chris Hadfield has a phrase, you never go into space with your fingers crossed. So we've taken out a lot of the ambiguity. James, do you have anything particular to add about the landing?
I think one of the pieces here is on the original Curiosity landing, there's an instrument system called Medley, and that was recording as much data as we could about what is the wind speed and pressure and temperature of this thing as it's going through. That really tells us, what's actually happening during this entry piece, because we can't actually communicate with the rover while it's going down there. It has to do this all by itself. It's so hot that the air actually ionizes, so there's no radio communication. Plus the time delay means that we can't even, when we see it's landed, it's been on the surface for 14 minutes already, either crashed or happily just starting itself up, and we just don't know. But so this time around, we've used the data from Medley, and I think there's the big upgrades that I was reading about were around the supersonic parachute, strengthening that, and I believe there's some heat shield upgrades as well around where the structure of the heat shield was designed. And we have a new Medley 2 instrument on there, which will give us even more data around what's going on, which I'm really excited to see. I don't know if Sarah or Lauren, any exciting pieces around the entry data that you can speak to?
No one's talked about the microphone yet.
Let's talk about the microphone.
Yes, there's actually going to be 2 microphones on the Perseverance lander. So the first one is actually to capture entry, descent, and landing sounds. So that's one thing that we wished we had with Curiosity, because you talk about this sky crane, you have this landing platform, your rover comes down on tethers and makes contact with the surface, and then this goes and crashes elsewhere and not down on top of your rover. Well, can you imagine the sound that makes when that crashes on the surface a third of a mile away? And to be able to, capture that and get these sounds from Mars, I think will be really exciting. And I'll just briefly say that the other microphone on there is part of the SuperCam instrument. So it will be able to capture the sounds of basically the laser making contact with the rocks, and also be turned on to listen to Mars wind and the sound of the wheels rolling across the surface, and other sounds from Mars. So I think that's an exciting part of this as well.
I think we also talk about the kind of tug of war between engineering and science around how can we get to the most aggressive landing sites, because that is where the most interesting science can be done. This data is crucial to doing that. So if I don't have the image, but if we have a photo of the landing ellipse from Curiosity versus Perseverance, the Perseverance ellipse is incredibly small compared to the Curiosity ellipse. That comes from a lot of these upgrades, and Lauren was talking about the terrain relative navigation and our ability to now do a range trigger on the parachutes, so that we can use that to steer where the rover is, and that lets us get to these more aggressive areas where we can get closer to where we need to go and not have to find a large parking lot that's perfectly flat so that we can do a safe landing.
Lauren, I think you've been asked by our producers to share your screen and describe the Mars Perseverance rover bingo. We have about 2 minutes and 19 seconds before entry interface. So go for it, Lauren.
All right, well, just to touch on what we were just talking about, the landing ellipse size here, I think is, like 10 kilometers or something, much smaller than we had for Curiosity. And prior to landing, the Perseverance team divided up the landing ellipse into these quads that are about 1 degree in latitude and longitude. And they named all of the quads after different parks and preserves of places all across the planet here on Earth. And then wherever the rover lands in here, and as we start to traverse, any rock targets that are selected for analysis will be named after geologic formations, mineral localities, important geologic features from these locations on Earth. So I think now might be a good time to, play landing site bingo. Where do you expect the rover to land, in which quad here?
All right, so Sarah says Sequoia or Tongariro. James and Max, do you have an opinion here?
I think
This one's the
living.
flattest.
I think living in Alberta right now, I have to go for Rocky Mountain. It looks like it is not anywhere near flat, but
yeah. We're about 30 seconds from atmosphere entry, and our audience, feel free to play this bingo and keep guessing where this thing is going to go. Zach, can we listen in? But the speakers, feel free to talk over it and describe to us what's going on as well.
We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars.
Right. So can someone describe to us what does it mean for atmosphere interface?
The is now waiting until it begins feeling the atmosphere of Mars slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
I'm just really, I mean, Perseverance has landed safely or not by now, and it's just like now we're waiting. Like it's already done its thing, but like we don't know, and I want to know now.
Perseverance. We have indications
it's got to be
that
scary now, right?
Now
when we get the atmospheric heating,
in the atmosphere,
that we also lose all information on what stage in the landing it's at. So it's only by simulation
the landing
now.
Target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
So the high-rise instrument on board the Mars Reconnaissance Orbiter is also hopefully taking
UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target.
Okay, so we're continuing. I can feel the nervousness in here. I don't want to talk. I just want to listen in. But we want to keep the panel going. And so we have a question from the audience, which goes around.
Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars.
Okay, we're getting close.
Heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target.
Okay, so I think things are going really great. I see smiles on our panelists' face. Let's go for a question. Hopefully we can get this done. It's going through the atmosphere right now, and just like an airplane experiences turbulence, does Perseverance also feel something like that? Yeah, so that's a question from one of our audience. James, do you want to talk to us about that?
Yeah, it definitely does. So the atmosphere on Mars, however, is way thinner. I think it's about 1/100th of that of Earth. So the same amount of wind speed will get 1/100th of the force on it. So it's not quite as drastic as what we see on Earth. But that doesn't mean that it's not significant. Looking at Curiosity's landing, the fact that they were going over different geological formations, the gravity field was changing, and that also plays into the flight path. So any amount of deviation is incredibly important.
Thank you, James.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Okay, the parachute has been deployed. That's good news, I'm guessing.
That was huge. I mean, that we just slowed down from going a kilometer a second to 100 meters per second.
To subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Right, so the heat shield separated as well, and now Perseverance has its first look onto Mars. That means it's starting to take pictures for the landing, right, James?
Yeah, I think Lauren can speak a lot more towards the terrain navigation system, but this is an incredibly exciting piece where it lets us actually understand the hazards before we get there.
Yes, yes.
Yeah, definitely. And I mean, I just look forward to getting all this data back and the record of what we're seeing during entry, descent, and landing. That also provides a lot of excellent context for this whole landing area for Jezero Crater.
Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Yes, we're going through it.
Crazy that we have a couple hundred kilometers and we started off at 12,000 miles per hour. I'm not sure what that is in kilometers, but then we have to reduce it down to less than one in a very short period of time. So this is 7 minutes of terror indeed.
It's almost like when you're on a plane and it's landing and you're like, why aren't you slowing down enough? I feel like the ground is like right underneath me, just like stop. And I feel like it's the same moment kind of.
Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Hey, I heard that the parachute has been separated.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
Here we go.
Tones.
As expected. As expected.
Sky crane maneuver has started. About 20 meters off the surface.
20 meters off the surface.
We're getting signals from MRO.
UHF is good. Touchdown confirmed. Perseverance.
Touchdown confirmed.
On the surface of Mars, ready to begin seeking the sands of past life.
We we have a successful landing.
At this point, the descent stage has flown away.
Oh, that's so exciting. I'm giving you all virtual high fives. Yeah.
Transmit direct through Mars Autonomous Orbiter to Earth.
Welcome to Mars, Perseverance. We're so happy to have you. And Ingenuity.
And Ingenuity, yes. Okay,
Yes.
so we see that the descent stage has flown away and Perseverance is continuing to navigate. This is great. Let's take in a few more minutes to just go through this NASA live stream.
All right, all stations.
We got it.
Touchdown confirmed. We're going to wait for the images.
Wow.
This is so exciting. The team is beside themselves. It's so surreal. Stay tuned. We might get some pictures.
Great.
We might get some pictures. And Lauren, tell us, are these pictures from the terrain relative navigation?
I'm anticipating we might get something there, and then also from the front hazard camera. That was one of the first confirmation images that we had on the Curiosity landing, where you just kind of see the terrain in front of you. It's a camera that's mounted on the rover's chest, so you can get front wheels and the terrain immediately in front. So let's find out where we landed.
Flattest place? Bingo winners?
Copy activity. That is as expected.
Once again, to our viewers, Perseverance is alive on Mars.
I did have some communication with the deputy project scientist for Mars 2020 prior to this, and she was feeling very nervous prior to landing and said, I really wish we had the airbags of myrrh right now. So I'm glad she's breathing a sigh of relief.
We're getting the first image.
Here we go.
Take a look at the first image.
Flight, this is OL3. I have the target point on the map when you are ready. We are ready, OL3. Go for it. Flight, I'll be moving in, showing you the safe zone that we've landed in.
Just put the first image from Perseverance on the surface of Mars. Now it comes from the engineering cameras known as the hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
All right, so hazard cam shows where we landed.
Beautiful, yeah. Looks like we have some broken blocks of bedrock there and some sandy cover. Looks like a nice flat area. You can see a bit of the shadow of the rover in there with the sun setting behind it. So good day on Mars.
Right. And let's talk about
Steve.
Max is happy because it's a flat part of the rover. Lauren, do we have an idea of where exactly it landed?
I do not yet. I was trying to take a look at that map to see exactly where, based on the terrain, I anticipate that it's out in the flat basin of Jezero crater, out where there might be either some ancient lake deposits, or another hypothesis for what some of these nice flat surface terrains might be would be potentially lava beds that have filled in this basin long after having had this, lake environment there. And so that will be one of the first things to test with the rover is what kind of environment does that surface represent right there?
Ooh, sorry, I was muted there for a minute. And so while this is going on, I'm very excited about this. Lauren, I'm going to lead in with you, and Max, feel free to chime in as well. Let's talk about how we communicate with the rover. How do we get the signal that Perseverance has landed, and where are we going from here when it comes to communications?
These cameras, but we took these seconds after
Max, I'll let you
landing,
dive in first.
For sure. So I'll talk about that, the quick one there of how do we know that it's safe, other than that hazmat camera there, a hazcam image there does show us pretty conclusively that we're safe. But how did we know before that photo came through? So there's with the Curiosity rover in particular, and it's similar on Perseverance, there are 3 safeguards they use to figure out it's safe. And that whole control room is probably hearing them trickle in as we were eavesdropping. So the first, you're looking for a touchdown sensor. So basically when those wheels hit the ground, there's now a force pushing them up and they're not going to be sagging. So you're going to have confirmation that, okay, the rover wheels have touched something. We know that. So that's one signal. We know we've landed. The second sensor is an inertial moment sensor, something that's telling you, is your object moving? It's the same technology that's in your phone that is the accelerometer that knows which way your phone is moving, or if you're driving, knows if you're moving at a certain speed. So they also have those on board Perseverance. So they're registering those to see if, have we landed? Are we sliding down a hill? Which that would register motion. So that was also presumably not registering any movement. And then also they're waiting for a signal from the rover, that telemetry, those just single beeps, as James was mentioning, for a little bit of time to make sure that that jetpack, the lowering part, the descent stage, has flown past, has not just cut its engines and fallen on top of Perseverance. So they wait a while to confirm that that stage has indeed flown away. And those are the 3 safeguards that let us know we have successful landing, and they knew to turn on the hazcams.
Yeah, and then the other part of that was kind of how does communication work between Earth and Mars? And generally we end up relaying information through the orbiters that we have in Mars orbit, and then those send information in terms of confirmation back down to Earth through the Deep Space Network, which is a series of antennas spread out all across Earth, so that whichever side is facing Mars at the time the signal is coming, we have a whole network to relay that information. But the rover does also have a direct-to-Earth capability for things like landing, which is how we got some of the confirmation now. But in terms of how operations will proceed after this, we'll be relaying information through the Mars Reconnaissance Orbiter, the Trace Gas Orbiter, and Odyssey, and potentially some other orbiters in the future.
Yeah, thank you.
And Nick, I think you're muted.
On that note, just while we're waiting for Nick there, Lauren, you mentioned the Mars Reconnaissance Orbiter being used to relay signal, and that's an incredibly important thing. Those orbiters, back to design life and aging of systems, this is space infrastructure. That's how we have to think about these. These aren't isolated projects. These are investments into continuing a human presence throughout the solar system. So the Mars Reconnaissance Orbiter was actually extended recently to have an additional term of life. I don't remember exactly how long it was, additional funding was provided for, but that's when you look at sort of a political level, you're funding high technical jobs to continue the sustainment of this infrastructure. We're not letting $1 billion orbiter just decay around Mars. We're continuing to invest in that orbiter, assisting future missions. So all of this should be better viewed as infrastructure as we continue moving forward into the solar system. Nick, back to you there.
Yeah, thank you, Max. Sorry, I've just been so excited with the landing. I needed to get up and walk around, and we had some sound difficulties, but I think I am back now and people can hear me. Yeah, thank you for that, for sure. Lauren, I want to get back to you because I have a very exciting question. And now that Perseverance is on Mars, what's it like to be on Mars time? How different is it?
Yeah, so the Martian day is about 37 minutes longer than an Earth day. So it's 24 hours and 37 minutes. And what the team is going to do is for the first 90 sols of the mission, they're going to live on Mars time to maximize the scientific return from this critical phase of the mission. So I did this when MSL and the Curiosity rover landed. And what it means is you're kind of rotating through every possible time zone. You're shifting about 30 minutes later every day for 3 months. And so you end up, being awake at a lot of odd times of day, kind of perpetual jet lag in some form. But adding to it, it's not just shifting 37 minutes each day. It's actually when we're getting the data back from those orbiters, relaying that data to Earth. And so you're constantly shifting backwards, but it might like jump forward a little bit and then back an hour, and then a little bit forward and then back an hour. So it's quite complicated, but it's a really special time on the mission. And yeah, I wish them well.
Yeah. That sounds really challenging indeed. And we haven't heard from Sarah in a while, and I want to get her back and her expertise into here. Sarah, you're an expert here about science outreach, and tell us a little bit about the Canadian contributions that have been when it comes to Mars mission or Perseverance, and what are you looking forward to the most when it comes to Percy landing on Mars now?
I think we've mentioned this multiple times that there's hundreds of thousands of people involved with every mission, and it's truly becoming more and more of an international effort nowadays. It's moving away from a competition or a race, and it's becoming more and more of a collaboration, which is really exciting. We've got some great folks in Canada that are involved. I mostly know of the scientists, sorry, Max and James. But we've got, as we've talked already, we've got Professor Chris Hurt out in Alberta. We have Professor Kim Tate here in Ontario, and a few more that are working on different parts. I know some that were involved in the site selection, for example, so on the science team for site selection, some on the sample selection, and of course we've got some companies that are working on building and helping with some of the instruments. But I just wanted to do sort of like a throwback, I guess, to the Phoenix mission, and talk about Canada's contribution to building sort of the LIDAR and the atmospheric station for Phoenix. Just a shout out that leave it to Canadians to discover snow on Mars. Out of everything that we could discover, we have to go and discover snow somewhere else. So it's really exciting. It's good to be involved. And, this is the third mission now that is getting to Mars in the past 10 days or 2 weeks. And I see on my Twitter feed from sort of like the radio and TV and the news as well, this one is the one that's getting the most attraction and attention, I guess, maybe because it's a rover, maybe because it's a bigger team, but they're all super exciting just to get there. And I'm so glad that, we weren't all sitting around here watching and be like, oh, well, that didn't go as planned. So I'm really glad it was a successful landing, and really looking forward to everything else that we're going to learn in the future years from Perseverance.
Yeah, let's do a kind of a poll here in terms of a question as we are now wrapping up this Perseverance landing party. Let's all the panelists, I would love to hear, what is it from an engineering point of view, from a science point of view, that you are looking forward to the most when it comes to Perseverance now that it has landed safely? How about we begin with you, Lauren?
Sure. From a science perspective, I'm definitely looking forward to learning about this past habitable environment, exploring, this delta on Mars. And I think the most exciting thing for me is knowing that the samples that are collected, we might one day get to see here on Earth. So that just adds so much more weight to the samples that are collected. So looking forward to that, and also hearing Mars for the first time with some of those microphones.
Yeah, Max?
I have to echo Lauren with hearing the sounds of Mars is definitely going to be an incredibly exciting thing. And for me, I know the most exciting thing for me is always the photos. As as connected as I am to the engineering, to those problems, and learning about lessons learned in those is always incredibly fascinating. It's always the pictures for me that make it, and those are the things that we all get out of it. We all will see what we want. I'm sure Lauren and Zara can see a lot more when they look at a rock than I can, but it's always incredible to have photographs from the surface of another planet. That's something I think we've only been able to say for the past 50 years. So that's pretty exciting.
Yeah, definitely. Another engineering perspective, James, what is it that you're looking most forward to when it comes to this event?
I think Max definitely took the big one is just it always shocks me whenever I see a photo from Mars and just that it's a photo from a different planet. It's not like I went out into the Badlands and took a photo. It is actually something in the sky that is floating above us. From the engineering side, though, there's a lot of new sensors and new data that we've collected, both during in the flight and also that we're going to be collecting on the Mars surface. So I think we talked a bit about the MOXIE system. There's a new weather station that's on there. And so I'm incredibly excited as we definitely do more, have more focus on human exploration to see how we can get this data and use it to get people on Mars at some point.
Yeah, and Sarah, I'm hoping you're gonna say we find alien life, but what is it that you're looking most forward to?
I'm looking forward to the unexpected surprises, good surprises. I feel like with every mission, there are things that we sort of anticipate and expect, and it's always exciting when we get them. But all of these rovers and missions have really surprised us. There are things that we don't really think about that that we end up seeing and discovering, and there's some sort of a different satisfaction in seeing things and understanding things that you weren't even expecting. So I'm looking forward to more positive, unexpected surprises.
Yeah, thank you, Sarah. Now that we have it, let's maybe take a few more questions from our audience over here. Eric McKinnon asks, what is the average budget for a rover like this, its operations, and who gives the fund? Given that, Lauren, you're attached with NASA a lot more, we're going to have you try and answer that.
Sure. So there are different classes of missions. And so this kind of falls into, that larger class of funding of mission. And so I can't remember the total cost for Mars 2020, but probably, a few billion. I think it was about 3 billion for Curiosity. But that's accounting for, all the infrastructure that goes into, building these rovers and getting them to Mars. And then there'll be more of an operational budget. So right now this is planned for a 2 Earth year mission. And then after that, it kind of goes up for evaluation again, and then you get into the extended missions. And so that's when more funding comes in down the line as well. Good question.
Yeah, thank you. Yeah, let's move on to, James, you want to?
One thing to add there, I often hear people talking about like why spend this amount of money to go into space? And one thing that I think is worth noting is that the money is spent on Earth. It is to hire people to do jobs on Earth, and it's to get information back and conduct good science. And ultimately, it is only benefiting us on Earth as well. So the things we learn about how to land on Mars and how to operate further away, there are Earth applications that come back to that. And same with the science that we're conducting here on Mars on trying to understand, was there life on other planets, has implications back on Earth as well. So the money is definitely well spent.
Yeah. And James, I want to stick with you over here as well. We have another question which sort of talks about how does NASA or any space agency test the range for these rovers, as in how far they can go on Martian soil?
It depends. So on Earth, we have a couple analog sites, and I'm not sure if Sarah or Lauren can talk a little bit more about some of the analog testing that different agencies do. But in terms of some past missions, for example, Curiosity, we have a duplicate of the Curiosity rover that we have on Earth, and there's plenty of testing that's done there. We'll use the best data that we have about Mars and create analog environments and just try them out. That's the best way to do the testing. Modeling can only get you so far, especially with the limited amount of sensors and past experience we have. So having an analog and really trying it out, putting it into weird situations will tell you all the information you need. And I think Max can speak to a lot of the over design that's needed as well, because there's only so far that you can get. So What you don't know, you just have to sort of predict the worst and design for it.
I was just going to say, very well said, James. I was only going to add, always build a spare. So it's good. It's good. But seriously, yeah, there is a very good value of having an identical copy of this instrument here on Earth to poke with a stick to see if what if we try this, and especially for now, for the coming weeks, if we're hesitant as we start to move the rover, as we start to articulate its limbs. But even down the road, I forget who mentioned it, but extended operations, what happens when we hit, the 6-year mark and we're still looking at a functioning rover, what can we do with it then? So that's when people get to be really creative. And one interesting thing is knowledge transfer in these projects. You'll have people coming onto these teams 6 years from now who never saw this thing here on Earth, but they'll work with it for years and years to come on Mars.
Yeah, I think that building a spare thing is a good thing. And if I'm not mistaken, Perseverance is something like 90% made out of the spare parts, the parts of the spare of Curiosity. And that's why it looks fairly similar to Curiosity as well. I hope I'm not wrong, but that sounds fairly familiar. So they always come in twos, I guess, sort of like Spirit and Opportunity as well. But going back to the question as well, that we always do analog testing here, whether it's to test a single instrument that's going to be put on these rovers or the rover in general. And there are a lot of places in Utah, for example, that look very similar to Mars. There's also the Arctic. We have craters, that we would take things to test out, and instruments, because the environment is very different, and we want to sort of test things in the extremes. So we always test them. Every single instrument gets tested in a vacuum environment. They do a lot of shake tests to see how they will survive sort of taking off and landing on another planet, but also rover in general as well. And again, with all the data that we have from Mars, we even know sort of the elevation of every part, and we can, when we want to map a path for a rover, we know how many degrees it would have to go uphill or downhill. And when the engineers give the scientists the limitations of the rover, it really helps them plan the path for the rover to move along as well. So for example, a rover can go only up 15 degrees or down 15 degrees, for example. So that sets the limitations of which paths you can follow. It's a lot of fun to sort of put in all the pieces of what we've learned about Mars, to put in those limitations, but also to work with with a big team to really figure out what will give us the best samples, what will give us the most science, what is the safest way, what do we do in case things go wrong, and to also test it out all out on Earth before we send a $3 billion thing into space. So that was a really, really good question too from the audience.
Yeah, thank you, Sarah. And I want to still stay with you here. We have another, I think that's a really great question. What is visible in the Martian sky? Sarah, do you want to go ahead and try and answer that?
It's a really good one. One of the funnest pictures that I've seen from, I can't remember which rover it was, but you can see the Martian moons. And there's actually 2 of them, unlike our one moon. So boring, we only have one moon. But Mars has 2 moons, so we still get to see that. We still get to see a sunrise and a sunset. And we get to see a lot of the stars. Now, they might look slightly different because of where we are located and where, Earth is located and Mars, but we still get to see a lot of the stars that we would see from here. We'd see the sun. But to me personally, the coolest thing is to see the Martian moons.
Right. Yeah, absolutely. Yeah, so that I think was our last question when it comes to Perseverance and questions from the audience. I do want to take maybe a few more minutes very quickly to talk about some of the future missions that, I mean, I know we have actually put some time into sort of the sample recovery and things like that. Is there something that maybe Max or James, you want to talk about specifically when it comes to the future missions that are going to Mars. Max, how about you start?
I think our landing success rate just went up a few percent. So that's what I'm excited about. But genuinely, these kinds of things, the fact that today has gone so well so far, and we'll find out in the coming weeks, how the rover's doing as it starts to function, as they do commissioning phases, making sure all the wheels work, make sure nothing broke on landing unexpectedly. But these kinds of things give us increased confidence as we move forward. I was joking about, always wanting to pick the flattest landing site, but, as we've talked about repeatedly, these increased sensors demonstrating that this technology works, and this has helped for a more pinpoint landing, a more targeted, we want to go here kind of thing, especially if we're going to land the sample fetch rovers and that future campaign of Mars rovers. If you look at a map of Mars, a globe, and you put dots where all the rovers are and landers, they're not next to each other. You can't see one from the other. So if we're going to build rovers that move, as James said, on the scale of kilometers in a year, we got to land these pretty close together if we're going to ever master Mars sample return. So the fact that we've got increased accuracy as we've landed, we've proven that technology today, and hopefully we see more of that in the mid-2010s with the next set of Mars rovers when they go. James, anything to add?
I think, Max, you kind of covered a lot of the really good highlights there. I think looking into the timeline in the future, I believe there's another rover landing in the next year or so. That's from ESA and Roscosmos. So we might be going through another 7 minutes of terror in 2022. But then I'm unsure about any of the other space agencies, but definitely there's been a lot more interest in Mars recently, at least for orbiters as well. So very excited to see what comes up next.
And I will add to James's comment there, the ExoMars rover that is being built right now by ESA, that's MDA, the company I work for here in Canada, built the drive system for that. So that'll be Canadian technology driving the ExoMars rover around Mars.
All right. Well, thank you, Max, for putting a futuristic perspective on our Mars exploration. I think that brings us to a close on this amazing panel. I'd like to thank you all panelists. So Lauren, Max, James, and Sarah, thank you so much for sharing your knowledge today with us. It's definitely been an enjoyable experience for me to learn about Mars so much. Studying galaxies, I don't think I come this close to Earth that often. So thank you so much about that. Yeah, I'd like to thank some of the people involved in the background as well. So Zach, our producer, thank you so much for being able to just switch and move things around so that our presentation on YouTube stays perfect. And then Mark Richardson, Sarah Sadowoy, and Connor Stone, who've been very integral towards the planning and bringing this whole thing together. And finally, I don't think this is the last thing. This is last, but definitely not the least thing. I would like to thank the audience. Thank you so much for joining today with us and sharing this enthusiasm and encouragement that we have for Percy and learning about Percy with us. This was a successful landing, but of course, this is just the beginning for some of the spectacular things that Percy will bring us when it comes to Mars exploration. But that's it from us. Thank you so much for joining. Bye.